Welcome to NSTA Web Seminars, where you can find live interactive learning at your desktop. Tonight's presentation is titled NGSS Crosscutting Concepts, Stability and Change. Our featured presenter today is Brett Moulding. We also have online with us Ted Willard from NSTA to provide information about NSTA's involvement in the development of NGSS. My name is Bryn Slate, and I will be moderating the program, and Jeff Lehman is online with us to provide technical support today. Before we jump in, I wanted to remind everyone to visit the NSTA Learning Center, which is your online portal for over 10,800 resources for science educators. And as many of you know, we have several thousand resources available for free. And once you gain access to a resource, you can have that in your My Library space so that it's there ready and waiting for you when you need to get to it. Our community forums are a great place to interact with other science teachers, and we have a forum that's committed to NGSS, so I encourage you to check that one out, pertinent to tonight's topic. Our online advisors are ready to assist you find the information that you need, and we also have free tools that can help you organize your professional learning and to meet and demonstrate your meeting of those goals. And it's all available by going to learningcenter.nsta.org. Right now, I'd like to introduce today's presenters. First, Ted Willard is going to start us off. He's our Director of NGSS at NSTA. And Brett Moulding is our featured presenter. He's Director of both the Partnership for Effective Science Teaching and Learning and Building Capacity for State Science Education. And I will, at this point, turn it over to Ted to get us started. Welcome, Ted.
Thanks, Bryn. Thanks, everyone, for being here tonight. For those of you who've seen some of our sessions before, these opening slides will be familiar, but just a chance to get us all a little bit on the same page here. The standards themselves were group work of 4 organizations: the National Academies of Science, Achieve, the American Association for the Advancement of Science, and NSTA. And there were 2 steps in the process for these standards. We had the work to develop the framework for K-12 science education that was released in July 2011. And as I mentioned in the chat a little bit ago, Brett was one of the members of the committee for the National Research Council that worked on and developed this framework. The second step was the development of the standards. Achieve coordinated and had 26 states around the country work together on those. Those states in blue, they were the ones who were the main participants in the development. They each had teams of reviewers to look through the standards and provide feedback to the group of writers. I should also mention that Brett was one of the writers for the standards as well. Now that the standards have been released, we're at the point where all of those states are in the process of giving serious consideration to those standards. They don't have to make use of these standards, but there already have been a great deal of interest. Just last Thursday night, the Rhode Island Board of Education was the first state to adopt these as their standards. So yay for Rhode Island out there. But other states are in the process of considering them in different ways. The states that were not the lead states, the states in gray, if you're from one of those states also have the opportunity to adopt these standards and are encouraged to do so. And so these standards then lead to development of assessments, curricula, instruction, teacher professional development, and teacher education, pre-service education. All of those come out and focus now from the standards. So the framework itself has 3 dimensions: the scientific and engineering practices, the cross-cutting concepts, and the disciplinary core ideas. And the standards, the framework recommends that these be blended together into performance expectations. If you haven't read the framework, the top of your list for summer reading once the school year's over is to read the framework. I strongly suggest you do so. You can get a free copy, PDF, from the National Academy Press, or you can order a hard copy from NSTA Press. The first piece, the scientific and engineering practices, those were what we focused on last fall. If you want to learn more about that, I suggest you go to some of our web seminars or archives from our series last fall, all listed through there. These are the things that students need to be able to do to really gain scientific understandings. And the cross-cutting concepts, what this series focuses on here, we're dealing today with stability and change, one of the remaining, but the other list here, we'll do a few more in the weeks to come. There are also the disciplinary core ideas, your traditional life science, physical science, and earth science, but engineering and technology in NGSS is on equal footing with these other areas. It really brings, a full-fledged aspect of STEM in together. And those different layers are worked down to finer grains, so matter and interaction is broken down into some more specific indicators and then even more specific standards themselves. And so the standards themselves, let's take a look at an example performance expectation here. This was one from the January draft. That developing molecular models of reactants and products to support the explanation that atoms and therefore mass are conserved in a chemical reaction. And this idea here blends together different elements. So we have developing and using models in the blue text, so develop molecular models to support an explanation. We have this idea about reactants and products and atoms and mass are conserved in a chemical reaction. And then down here, the total number and type of each atom is conserved, and thus mass does not change in a chemical reaction. And then the cross-cutting concept of matter being conserved, and this idea of conservation tying into one of the cross-cutting concepts. It's important to note this performance expectation here is a description of what is to be assessed at the end of instruction. It is not requiring that this be the specific activities that go on in the classroom. Teachers can make use of their own judgment about what is the best way and how to use multiple practices to get students to understand certain ideas and to be ready to show their knowledge through performing this performance expectation. And so with that basic little outline there, I'm going to turn things over to Brett, and so we can hear more about stability and change. Over to you, Brett.
Thank you, Ted, and good evening. I appreciate that so many of you took time this evening to listen in on the web seminar on stability and change, one of the cross-cutting concepts. I hope we have an opportunity to talk about some insights that come from the framework for K-12 science education, as well as how these play out across the NGSS assessment standards. So, as Ted said, I'm Brett Moulding. I have been involved with these standards from the time that they were just being discussed. If you look back on this set of standards, it has a nice trajectory that moved forward from taking science to school, and even before that, both the National Science Education Standards and the Benchmarks for Science Literacy. So tonight, what we're going to do is this quick little run through here. Why stability and change? Why is that a cross-cutting concept? Give you a little bit of logic behind why this is a cross-cutting concept. Talk a little bit about the NRC framework for K-12 science education in terms of the vision for science education, as well as cross-cutting concepts. We'll then move into stability and change specifically as a concept that crosses all of the disciplines of science, as well as the thinking in science education for many, many years. And then we'll have some time for discussion. I have a couple of stopping points where we're going to stop and pose some reflection and see if we can get you to think about some things and ask some questions as well. So let's get started. I don't know if you know this or not, but I live in Utah, and in Utah we have Hoodoos. One of our 5 national parks that we have in Utah is Bryce Canyon National Park. And here's a picture of a hoodoo there called Thor's Hammer. This is a picture at midday, and it's a beautiful geologic formation in southern Utah. One of the reasons I'm so interested in this particular one is it gives us a nice chance to look at change playing out over thousands and millions of years. These particular things called hoodoos that exist in several parks in Utah, national parks here in Utah, have come about through change. So if I'm going to think about any part of science and understanding concepts like geologic change, one of the things I need my students, or I'd hope my students to be able to do, is understand things like how does this change and what is the rate of change that would occur. We're going to talk a little bit today about the fact that things change. Here's another hoodoo. It's called Sentinel. And this particular hoodoo, this picture was taken before it collapsed in 1973. And so the change there was very dramatic. But leading up to that change has been a slow, gradual change that has occurred throughout Bryce Canyon National Park. All of these surfaces in Bryce Canyon, because of the soft sedimentary rock that they're built in, are currently weathering at a rate of about 1 centimeter a year. Now I want you to just think about something. Here's this rock structure here, and it is weathering at 1 centimeter a year. If you think about the photography that we have available, and when it first started taking pictures, there are pictures from 100 years ago of Bryce Canyon National Park, and those pictures, if you think about if it's going at 1 centimeter a year, that would mean that over the course of a century, 100 years, you would have a meter change. That's not a meter change in height or width, that's a meter change at every dimension. That's significant change that has happened to a rock structure here in Bryce Canyon National Park. When we think about geologic time in particular, we think about millions of years, but some of the changes happen in shorter time frames, and but they're both related to this idea of change. We're going to talk about change a little bit more tonight than we will stability. And one of the reasons why we're going to do that is because we kind of think that stability is a special case for change. So why stability and change? Why did it make the list of 7 cross-cutting concepts? One of the reasons was that it came from a nice trajectory of documents that occurred previously. The benchmarks and National Science Education Standards and the 1996 NAEP framework all had change as one of the key concepts that were to be either a unifying concept or a theme in those documents. So those standards or frameworks had that as an idea. So when the framework for K-12 science education was developed, it is based on research. And so one of the elements of what played into it was, is there a trajectory that came from someplace? Did this idea of stability and change have roots and has had any utility in the classroom? One of the things about stability and change is the idea that is change certain. Do you ever ask yourself that question, is change certain? Well, we have to look back on geologic time, but also the life on Earth to have the idea that change is certain. Things change. One of the things about change is that it has a relationship to the concept of time. If you think of change and relate it to time, you'll find students begin having a number of problems with this, and the research shows that students have a difficult time understanding change over long periods of time. And we'll talk a little bit more about that throughout the presentation this evening. The concept of stability appears in the benchmarks, NSES, and the 1996 NAEP framework. The way that it was described in all of these documents is in terms of the equilibrium concept, and in life sciences through homeostasis. But it was also called out as one of the unifying concepts or themes. So change has a history, and evidently they decided in the development of the framework they wouldn't change it. Stability and change, constancy and change. The idea of constancy and change came from the AAAS benchmarks for science literacy. Constancy and change is included as one of 4 common themes. So in the benchmarks, there were 4 common themes that appeared. In the framework and the next generation science standards, there are 7 cross-cutting concepts that play out. In the National Science Education Standards, which was released in 1996, the idea was unifying themes and principles, and they included constancy and change as well as evolution and equilibrium. And they spent quite a bit of time talking about evolution as one of the forms of change. Change as a natural result of time appears in all of the standards. If you think about classrooms and have discussions with students, they begin having a difficult time understanding how changes that happen over a long period of time occur. They relate to changes that occur on short time frames, looking at day-night cycles and changes that happen over short periods of time. So change as a natural result of time means that instruction should relate change to time, and the way we generally do that is the rate of change. So the concept of rate of change plays out in the next generation science standards. The middle grade levels, it's emphasized as several of the grade levels as one of the important concepts that all students should be able to obtain and have utility with. Stability is the other piece that is related to time. At one scale of time, things may be stable, but over a longer period of time or at a different scale of distance or number, stability doesn't exist. So whenever we define stability, it needs to be in terms of stability related to a time scale. The rocks in the east are made of granite, hard rocks. Even those rocks over time will weather and erode away. A chemical reaction process that happens in a long time frame will happen in a shorter time frame with a catalyst. So what would be a stable situation or an equilibrium situation in a chemical reaction with change can become an unstable situation and a shift occurs. So we've had a little bit of time to introduce some ideas here about stability and change and where it came from. I thought it'd be nice to have a little bit of reflection, and maybe you can chime in here on the talk window or ask questions about an example of a science phenomenon in which the concept of stability is useful for students to construct an explanation. So let's share some of these ideas about the usefulness of it in the classroom, as well as any questions you might have. Ted, are you going to moderate?
Yeah, I'll be happy to. So we've got a few examples that have been put up here. Amanda mentions noble gases, Caroline homeostasis. We've got Eleanor mentioning the seasons, global warming, Earth's orbit. Another example mentioning the seasons. Different ideas about the Earth moving around the sun, or looking here, see if we have any questions as well. Are these some typical examples that you've seen before, Brett?
Yeah, this is kind of interesting. You know, we're looking at examples of stability, and as I'm looking in, I like the idea that someone has identified law of conservation math and law of conservation of energy. And thinking of that as a principle, it's a principle of stability. And in fact, the change being stable is one of the things I see in a number of pieces here. The solar system is another good example. We think of that as a system in equilibrium, and yet our moon is slowly leaving us, is going out of orbit slowly over time. So there's change there. But in terms of the way we look at the moon being stable, in a stable orbit, and the sun, Earth, the solar system being stable, it's stable on the sort of time frames that we think about. The rock cycle, they show the rock cycle is one that people mention, the rock cycle, and as being a stable concept, a principle of change over time, but the process is again stable. And I noticed that someone mentioned Newton's laws. We're talking now about stability of the concept and not the stability in nature. We're looking at applying our rules of describing how those things would occur. So this is very interesting. Did anyone have any questions that they would like to put forward? Ted?
Yeah, I'm looking and don't see any questions right now. I was just thinking about your point about stability, but this aspect of changing with stability. That Newton's laws are stable over a certain range of phenomena, but when you get to certain outside of those boundaries, extremely high speeds, large masses, things like that, again, you get that change in the stability that you were discussing as well, with some things being stable over a certain period of time, but not over longer periods of time.
Well, and the size of the particle that you're describing, Newton's laws had to be, readdressed when we started looking at very small particles. So again, stability at one scale, and that's a good example of it, stability at one scale is not stability or at another scale. Some laws that hold at one scale change when we move to a different scale. These are pretty interesting ideas that people are putting forward.
Victoria has an interesting question here. She's asking, what do you mean by stability? Is it a constant or can it be a variable?
Well, that's a good question. And when we get to the standards, you'll see that quite often the relationship between stability and change is one that is connected through cause and effect relationships. So when you look at what is described in the framework and Next Generation Science Standard, most of these ideas have relationships to other ideas. In other words, you don't have stability and change standing alone. It's stability and change as it relates to cause and effect relationship, as it relates to systems. So that's a good question.
Deborah had asked about some life science examples, which then some people suggested life cycle, or this Victoria asking, can a food web be seen as a stable system until acted upon?
Yeah, and that is a very good example of what we put as a model of a stable system. That's the other part of it. For us to understand the life science, we oftentimes establish what we would call a stable system, but it's a model of a stable system, and it's easier for us to study it if it is stable. Ecosystems are not stable. Food webs are not stable, but unless we put them into the model, and then we can study them easier in that situation. One of the simplest ideas of thinking about stability in life science was, in fact, the ideas surrounding homeostasis and the feedback mechanisms that happen within living organisms that allow that to happen. We can also think about change as being stable. We have a stable change process. Seasons change in a cyclic fashion. We'll talk more about cyclic change, and the idea of cyclic change may in fact be what we refer to as stable.
I'm also thinking about the idea of constant velocity. Velocity is a change in something, but it's the same change every unit of time if you have a constant velocity. So that there is some, as you said, some interconnectedness here. It's not like they're totally opposite sides of a coin. They actually relate to each other in a number of ways, stability and change.
And the question becomes, how does this play out in the classroom? So let's move on a little bit and have a little bit of a conversation again later in the presentation. I want you to be thinking about the part of this is, how does this play out in the classroom?
Yep.
By the way, I just saw one of the questions about the biosphere in southern Arizona. I think was an interesting idea. That is this an experiment in stability, trying to establish an ecosystem within a stable system. So I thought that was an interesting idea. Here's some ideas. You know, climate change was put forward. Evolution is a change that happens in science. These are some of the big ideas we're dealing with. Expansion of the universe is a constant change. And long-term ecological changes, they're changes. Geologic change happens. Chemical and physical changes happen. So change in science is something that we make great utility of. It has a lot of purposes. And in the NGSS, it appears in many of the performance expectations. I just opened up the NGSS the PDF file and put in my handy-dandy Macintosh computer how many times does the word change appear in the Next Generation Science Standards. And it appears over 100 times. My computer wouldn't tell me exactly the number, but it said over 100 times. And I found that it also appears in many of the performance expectations. So when we ask questions and predict outcomes about the changes in energy that occur when objects collide, in this particular performance expectation, changes is the key concept that students are working with in this topic. So changes become central to this particular one. Construct an argument supported by empirical evidence that changes to physical or biological components of an ecosystem affect population. So it's the changes of the system that affect the populations. So again, the concept of change becomes very important. And in high school, analyze geoscience data to make the claim that one change of Earth's surface can create feedback that causes changes to other Earth systems. So again, the key here, the action, the thing that students are to think about are the changes. And how do we go about helping students understand concepts related to change? In the framework for K-12 science education, there's a vision for how these things should play out in the classroom. Change and stability is just one of the concepts that should play out in this way. So I thought I'd take some time and go through the ideas there in the framework for K-12 science education and see if I couldn't shed some light on some of the ideas that came out in that vision for science education. We have the 7 cross-cutting concepts, and perhaps the most important part of that is that they're concepts. They're cross-cutting, but they are also concepts, and that part of it plays out as a very important part of what should be played out in the science classroom. The framework is designed to help realize a vision for science education. And the vision is progressively deeper understanding of science, students actively engaged in science and engineering practices, and they're doing these practices in order to deepen their understanding of cross-cutting concepts and disciplinary core ideas. So the practices serve the role of helping students to deepen their understanding of cross-cutting concepts and core ideas. And then the framework makes it very clear that in order for that to happen, and it should all of the 3 dimensions need to be integrated into performances. It's not sufficient that they should be taught independently and separately. They must be taught together for that vision to be realized. And again, here are the 3 dimensions. And again, the document is stating for them to be woven together in each of the areas in standards, in curriculum, instruction, and assessment. So if we're seeking this performance by the student, the standards, the curriculum, the instruction, the assessment must facilitate the student's performance. And I like to talk about this as a performance by the student. It's not what the teacher's performance, it's the student's performance. The teacher's role is really to create the situation so students will be exposed to a lot of science phenomena and be able to perform with using all 3 dimensions, the science and engineering practices, the cross-cutting concepts, the disciplinary core ideas. And the performance happens in the classroom, but more importantly, the student takes these cross-cutting concepts, disciplinary core ideas, and science practices, and are able to use them when they encounter novel phenomena. And that's really kind of the interesting part of this that I would hope that people would begin understanding is our instruction needs to lead to student performances. If we were teaching music, we wouldn't teach the students about the number of keys on a keyboard, and I think there are 88, but that's not the performance. A student being able to tell you, well, there's 88 keys on the keyboard is not the performance. Knowing that the pitcher's mound is 60 feet 6 inches away from home plate isn't as important as being able to throw a strike. So the performance in baseball would be throwing a strike. The performance in science is doing science. It is engaging in the practices, conducting investigations or arguing from evidence or constructing explanations, and using cross-cutting concepts and disciplinary core ideas to do this performance. So the vision for science education, described in the framework and played out in the next generation of science standards, which are assessment standards, is in fact the performance of students in science. So the role of teachers and administrators and all other parts of the system for science education has to be to create situations where the performance can happen and happen in meaningful ways and in a way that students carry forward when they encounter novel phenomena. So this cross-cutting concept scaffold across a number of disciplines, but they're about sense-making. And science is a lot about sense-making. We need to make sense of things, reasoning. And the cross-cutting concept is one of the powerful ways that we can make sense. If we think about stability and change, we're using that concept to make sense of things. We're not using the concept to memorize what change is or a definition. It's to understand the novel phenomena that students encounter every day in their life, or it's to understand concepts in the science classroom. The important part is that students need to have instruction that makes these 7 concepts clear to them and explicit in the classroom without teaching them as a separate set of content. They're what students will use to make sense of the world. So it needs to be that every student, not just the teacher, understands what the cross-cutting concepts are. When we're talking about change, students should understand the concept of change and how it relates to time. And the cross-cutting concepts have great utility for instruction. They're not just something that you have them learn. They have great utility for instruction. They become touchstones that we would hope that all students were able to utilize. And they only become useful for students when they become explicit references to the concepts in all of instruction and instructional materials. And it's not that there's a chapter in a book or there's a unit on cross-cutting concepts. These need to be integrated in each of the performances that students engage in throughout their science experiences. So, we talked earlier about stability and change. We moved on to a little bit of a placement of cross-cutting concepts in the instructional component of instruction. So what are some effective ways to bring cross-cutting concepts in the science classrooms and in science instruction? So give us some specific examples. That means you're going to have probably more than 2 words on this, so we'll have plenty of time. We also have an opportunity at this point in time to have some questions. And if you can make your examples specific to stability and change, that'd be great. But in general terms of cross-cutting concepts, what are some effective ways to bring cross-cutting concepts into science construction? Ted, will you moderate this for us?
Absolutely. So our first example put out here is tracing energy in systems. and the folks are giving some examples here. I think you're asking not just what the examples are, but also how you would bring them into science instruction, so folks can include that in their descriptions. I think that's great.
And that it really does need to. I want us to think about instruction. That's our role as teachers, is instruction. And so let's talk about the way that these can be used in instruction.
So folks are writing down some pieces here. I'm trying to think about that first example here of tracing energy in systems that you might be asking students to think about the energy a system has, or several different systems have, and how that energy either moves from one system to another, or how it is transformed within a system, from potential energy to kinetic energy, as an example.
Well, I just saw one of the ones I picked up on there was someone talking about the change that occurs and how much energy it would take to lift a mountain up, and then how much energy is returned to the system when that weathers and erodes away. So the instruction might in fact be models and modeling of that change. So your practice might be modeled, and your cross-cutting concept of change could in fact be looking at that idea. So, but I would hope that the instruction would be done in such a way that the students would be able to know that we're looking at change here. It's a relationship, and it's a model, but we're looking at the changes that occur in the model. Let's see, there's one here with a smiley face, so you might pick up on that one, Ted.
Oops, sorry, it didn't move down here. I'm sorry. My scrolling had stopped. Victoria's point here about starting broad with general students, asking them broad questions and developing their own theories about something. So second graders think the Earth is made out from a center to where we are. Many of them come up with a theory of layers on their own. So that idea of structure coming into place here.
I see them.
Go ahead.
Speaking of change, I accidentally clicked off when I thought I was clicking. I saw one of the pieces there was in the class discussion or discourse, and they're talking about a talk and argument. Talk moves. The talk moves are excellent places where teachers have an opportunity to extend students' thinking. When students give you a concept, then focusing on what changed. Well, what has changed in this concept? What evidence do you have that change has occurred? What caused the change to occur? And so I think that one of the nice places in instruction to have these things happening is, in fact, in classroom discourse. And classroom discourse isn't limited to the teacher and the student. Well, the best classrooms I've had an opportunity to observe are the ones where students are asking each other about what is changing and what is stable, and one student talking to another. How do they pick up? How do we get our students to the point where when they ask questions, they are asking questions about what has changed, what has stayed the same? Yeah,
Gabriella's example, I was going to say just as you were talking, I think hits on some of the same points here. Asking how a particular phenomenon is an example of change, and then what is changing. She brings up the example of the water cycle. Students could explain how water changes, it moves in that, quote, cycle.
And what causes the water to change.
Feeds into a number of different questions here. Jennifer here making this point about kids doing science, not memorizing what you had just brought up as an important point here, is that I think even in some of these examples, it's easy to start to see the connections between cross-cutting concepts and some of the disciplinary core ideas, but moving into the idea of the practices, particularly students engaging in the practices and linking that is I think is what's really new in these standards. and something that...
Well, and so one of them that just rolled by is discussion about the New Jersey shore and the change that has happened there and the causes of those changes and how stable are other shorelines and the new shoreline that exists in places, how stable will that be? So making these connections to local things, having cross-cutting concepts connect with what's happening locally, whether it's a tornado or a hurricane like superstorm. All of these pieces that happen in students' daily lives or are connected or are interested in are good ways to help students, understand that what we're looking at here is a change in a system.
Yeah. I also liked Lauren's comment earlier about in teaching in different subjects, both within science, we sometimes think of life science, earth science, and physical science as different disciplines within the overall subject of science, but also getting into literature and how some of these things change comes up in there and making those connections.
And Catherine mentioned that it's very important to discuss an investigation after doing an investigation. So what does this discussion in an investigation look like? It's looking at the parameters of the practices, but it's also looking at what has changed in the investigation.
Absolutely. Very good here. Right, so some other examples here. I want to check and make sure if anyone has any questions for Brett, we can also take some of those here. Glenda is an example of having students construct design, and I like this point, justify reasoning behind such a structure. Making models of different types and what you've learned and how would you structure them differently and why based on new information.
Well, and the other question that becomes important is what evidence do students have that change has occurred? And the idea that the students can often use the change as the evidence to support an explanation.
Very good. Just checking here one more second. We've got some nice feedback between folks. You want to move on here for a bit and we can then carry on some more conversation down the road.
Victoria's commenting here, I love having my students justify their answers, watching the shock in their faces when they realize they have to explain why they think what they do. And one of the things that I'm sure that their students will do is support it with evidence. Using that terminology, of the standards is sometimes very valuable for students to talk about change as evidence of what caused something to occur. Okay, let's move on. So again, here are the cross-cutting concepts. They don't stand alone. That's one of the pieces. You don't just look at stability as one of the concepts without it having specific relationships to other things. One of the things that I tend to do is 7 is a lot, and so I think it's important for us to make sense of these cross-cutting concepts and put kind of a sense-making together. The framework does a little bit of this, and there's appendices in the Next Generation Science Standards that talks about this idea that we're about to talk about here, and that is that how do they make sense? How are they related? In my way of thinking of these things, causality, cause and effect, is, since it's so central to understanding science, it is one of the core ideas. If we don't have a cause for something, it's not science. And so what we're looking for in science is causes for things that have occurred. And the other important idea that we have is that systems are what we're studying. And this cross-cutting concept of scale, proportion, change in stability, matter and energy, and structure and function fall under that idea of systems. That's how we define our systems. That's how we describe our systems. Systems are described in terms of these attributes of the things in the system. And then the cross-cutting concept of patterns is a very powerful tool that we use for understanding the causes of things. Patterns are quite often used as evidence to support explanations or develop an argument. So when we look at these three here, the 7 concepts into these 3 areas, this is kind of the thinking that goes into how do we make sense of these things and what are their roles in helping students understand how the 7 cross-cutting concepts play out. I remember them in terms of this diagram. It makes sense to me, and it has quite a bit of utility. We have an opportunity to work with a lot of elementary teachers in our professional development here in Utah. And one of the things that we spend a lot of time with is helping them to engage with students in all 7 of the cross-cutting concepts. And this has been a useful tool for them to remember kind of the role of those in the discussion. And again, these 3 ideas are around phenomena. So we're defining a system to investigate. We're looking for causality. What has caused that phenomenon to occur? And we're using patterns as evidence. If I look at a rock formation, it has a pattern. Something caused that pattern to happen. Some sort of change happened in a system a long time ago for that pattern to occur in that rock formation. If I look at an ecosystem, that system is defined in terms of the matter and energy into and out of that system, and the relationship between what happens in that system, the changes that happen over time. If a system becomes less stable, the ecosystem has to have a cause for that change to occur. And we can look for patterns to help describe those things or evidence to support an explanation we might have for that. But again, it's around that phenomena. And the phenomena is what students are performing on. They're constructing explanations, they're arguing from evidence, they're engaging their core ideas in supporting their explanations. All 3 parts of the framework, practices, cross-cutting concepts, and core ideas play together when students are in these performance modes. So cross-cutting concepts are about making sense of things. Geologists have found patterns in rocks, layers. Sedimentary rock provides evidence of change over time in what happened to be a stable, what appears to be a stable condition. So geologists have always used these ideas of change in systems based on the idea that the evidence lies in the patterns. The framework describes these the stability as the conditions in some aspects of a system are unchanged, at least at a specific time scale. Stability means that small disturbances will fade away. Such as stability can take a number of forms. We don't always have just one form of stability. When we think of stability, we need to think of it in terms of a time scale or in terms of scale of size or distance. Systems with steady inflows and outflows are said to be a constant condition. It's really dynamic equilibrium. In Utah, we have a number of salt lakes. There's one particular one called the Great Salt Lake, and out there's solar ponds that they use to mine salt and other salt, minerals. And the process is one of dynamic equilibrium. They put salt water, very concentrated salt water from the Great Salt Lake, in an evaporation pond, evaporate water so that the salts become increasingly concentrated, and the level of concentration becomes very high. Some of the salts, the ones that are the least soluble, the magnesium salts and others, will precipitate out of solution. They then move the solution onto the next pond and then move in some more water. So they're precipitating out specific salts in each pond. That change, that stability that happens is a constant, so they can calculate when the salts would fall out of solution. So the solutions move from pond to pond to pond, leaving behind one of the types of salts in that pond. They then come in and they pull those salts up, and some of them are very valuable salts, potassium salts, phosphate salts, a number of them. The ones with the highest solubility are the ones that precipitate out of the last pond and are the most concentrated in that particular mineral. That is using that principle of equilibrium and the idea that there is a precipitation that happens at a certain point when the equilibrium shifts. And that whole concept is based on that idea of stability and change. Someone mentioned earlier the idea of stability in cycles. Repeating cycles can be considered, repeating cycles of change can be considered stable. And we describe them that way, and it helps us make sense of the world in terms of stability when we allow cycles to be considered stable. Systems systems that have constant aspects to them, such as the moon and the pattern of phases over time, these are thought of as being stable as well. Regardless of how long the cycle is, if it has a cycle, it can be considered to be stable. And the other part of it is oftentimes we try to design stability. We put zinc metal onto iron so that it stays stable for a longer period of time. It is changing. The zinc is slowly oxidizing off, but we don't see the rust of the things that were zinc coated, like a galvanized nail. We've designed the stability, we've engineered it. So design stability, even though oftentimes it's not as stable as it would, we might hope it would be, it's still stable. We would hope that our bridges would be stable, and they're designed to be stable over a certain period of time. But again, given enough time, they fail as well. Things like float tanks and overflow valves are other examples of engineered systems that help us to keep things stable. Again, stability and change are always connected to time. And I can't think of an incident where it doesn't. One of the interesting things about time, though, is deep time. Time is over long periods of time are very difficult for us to conceive of. I often think that geologic time is nearly inconceivable. It's so hard to put it in a scale that makes sense. And so this idea of change is very much related to scale. And it kind of makes us, when we think about those periods of time from the evidence we have in current day, it gives us a funny feeling about, these changes have happened in the past. They will happen in the future. And we're witness to one little episode of that happening. So when we look around the world, we think the mountains are stable. But in fact, given enough geologic time, the Rocky Mountains, which were uplifted 500 million years ago, are not that stable. If we look at causality and change, we really think of it in terms of every relationship has a cause and effect. Practice of constructing explanations for phenomena often focuses on describing the mechanism of the observed change. In the standards, you'll see the word how occasionally. In a performance expectation, it's really asking what is the mechanism. And you look at it quite often, they're connected to a cross-cutting concept of change. How does this happen? How does this change? So causality is very strongly related to change in the way we understand concepts. Systems, again, stability and change are often used to describe the system. And we might ask questions of students like, how is the system changing? What is the rate of change of the system? How is causing the change? What is causing the change in the system? Those are all useful questions. And oftentimes, good instruction requires that we plan our key questions. Our punchlines to our jokes will have to be set up by a straight man, and the question is really the science teacher's straight man. And these are just a few of the questions related to change. Observing change in systems is an important way students are able to determine patterns. So patterns are related to change, and many patterns, change is what is looked at. It's not the pattern doesn't exist unless we look at the rate of change. So oftentimes when we analyze data, we're looking at putting data in a form that the change or the rate of change that happens in the data can be seen more easily, because that's what makes sense on any time scale. Sorry, I just lost track of a few things here. So this brings us to the discussion and questions and the chance to close this. But I would hope we'd have a nice discussion here, and we're open to questions. Ted, are you going to moderate this part of the program?
Sure, I'd be happy to. I'd like to start maybe with a question that came up a little earlier. Kelly was asking about at what age do you think students can grasp a difference between static and dynamic equilibrium? As Scott said, I wrote a little response there. I was thinking that it might depend upon the system, that the number of people in a room might be easy for students to understand as a static or dynamic equilibrium, but the amount of energy in the atmosphere might be a much harder thing to understand as a dynamic equilibrium. I don't know what your thoughts are on that. Your mic may be turned off right now, Brett.
Sorry. Can you hear me now?
Yes, I can. Thank you.
Oh, sorry. Children in kindergarten are learning about dynamic equilibrium and stable equilibrium when they are, in fact, learning about change. One of the things we always look at in the next generation science standards is this trajectory or progression of learning. The progression includes the steps that we would put in place so that children would understand increasingly more complicated concepts of change based on the things that they begin learning at early grades and relating it to things that are in fact at a scale that makes sense to them. So we wouldn't want to be looking at scales that are not easily observed or understood. I would hope that they would be looking at scales that are at the size of the student and that time frames are within their purview. And so that's a very good question. When do you begin? The preliminary steps are, in fact, when they begin talking about change in the early grades.
So we've got some discussion about, I'm trying to make sense of Matthew's comment here about suggesting copper, is it sulfide or sulfate, SO4? I'm a physicist, not a chemist. Good experiment even in kindergarten and up. Sulfate, thank you.
I don't know if I would use copper sulfate with kindergartners, but if they're going to get involved with it. But there's a lot of ideas related to solubility that we learn early in our life. And part of it is how much will dissolve in a solution is a solubility concept related to equilibrium.
Yeah, I think the rock candy idea would probably be a safer one.
Yes, that's a very good idea.
The kids will probably like it better too. just rolling back here a little bit, trying to look at a little bit of talking about energy, and I think this key is at least one of my takeaways. It's sometimes the cross-cutting concept itself, or the idea of stability or change, isn't in of itself complex. It's that the system that we're talking about is a relatively complex system. There may be aspects of the system that are not readily apparent to someone looking at it. So for example, when you're talking about energy, you can't see energy, so it makes it harder to understand some of these ideas about stability or constancy and change. What questions do folks here have for Brett about some of these cross-cutting concepts, if we expand a little bit? I really have to say, I really love the grouping that you showed us tonight. I saw some examples of that from some of your presentations at the NSTA conference in San Antonio. But pulling some of these things together made things that make a lot more sense to me about the cross-cutting concepts.
One of the questions here is there a source of lessons that show how these next generation science cross-cutting concepts play out? And that's really the question on the agenda. I know that in Georgia and in South Dakota and other places, currently they're looking at instructional activities that engage all three dimensions, and particularly the cross-cutting concepts have had great utility in helping students make sense of phenomena. And so that's a very good question. Where will the instructional activities come from? And part of it early on in this process will in fact be people looking at what they're currently doing and asking the question, well, how will I engage students in these performances? I've oftentimes said, when people ask me, when should we begin implementing the next generation science standards, I said, well, first of all, they need to be adopted, then implemented within a state. But this vision for science education that comes out of the framework, the idea of the three dimensions, the concept that students will be performing science, and that there are these three components of the science performance, should be implemented now. It's what research tells us is the way students learn in a way that they retain, and it should be what we're doing currently with whatever standards you have or engaging the students in. It's not the idea of a performance and bringing three dimensions to bear, and having a kind of a definition of these three dimensions makes this performance something that can be done now. So regardless of your state's current standards or the timeline for adopting the vision for science education, the way science instruction happens to get to the science performance, I think should happen now.
So that's a great point, Brett. I heard a lot of folks talk about making use of the practices in their instruction at this point and doing that. But if I understand you right, you'd also recommend that when it comes to the cross-cutting concepts, that people would be great for teachers, to start as soon as possible to, pay attention to these cross-cutting concepts and flesh them out for their students at times where the connections can be made. Am I understanding you correctly?
So that's exactly it. Well, it's not exactly it. I think what starts with is this idea that there's a performance. But the cross-cutting concepts in particular, it's hard to do any of the practices without engaging the student, having the students understand the cross-cutting concepts. Because when they're constructing an explanation, they're really constructing an explanation about a system, and they're using cause and effect relationships and using ideas of change to study what's happened to the system. So if a student doesn't understand ideas of change, how are they going to look at data and make sense of that? And when they look at data, when you do a nice investigation and the students generate data, do they know that they're looking at the change that happens over time? in that system that they're studying. And those are the kind of subtle pieces of classroom instruction that have great utility and students can make sense of very quickly, provided the instruction returns to it regularly.
Mm-hmm. So Kelly Lynn has a question here which I think is important for us to touch on here. She says, quote, I heard someone misspeak at the STEM conference in St. Louis. Brett, the PE are not the standards, correct? Would the DCIs be the standards? And do you want to comment to that?
Standards are as much political as they are academic. The performance expectations are what students should know and be able to do. Those are the things that are assessed. So what are the standards? Depends on how your state defines it. Most states have in the past defined their standards as the student's performance, what all students know and can do. And so the performance expectations are the standards. Some states might define them broader or narrower, but the performance expectations are in fact what many states will use as what they'll describe as the standard. Because that's the standards of what students can do, what they know and are able to do. And if you read the document, that's what is built into the assessment standards in Next Generation Science Standards.
Great, thank you. Another comment here from Matthias. Is the focus on cross-cutting concepts a little too brainy in the beginning? Should we begin to let them just sense the fascination of phenomena they come about first and wonder why?
Oh, yes, they should always, you should wonder. In science, you should wonder. I agree. But I think that there should be some tools to wonder with and asking questions about, well, so what changed? And so I think the cross-cutting concepts are actually the tools that help students to wonder and question phenomena that has happened. So, but I like wonder. I think if it wasn't for that, few of us would be interested in science, but that chance to wonder. But I, again, believe that the wonder needs to have some tools to help structure it so students can, engage in deeper questions and just the aesthetics of what they're observing.
So, as a physics teacher myself, I buy into Sarah White's comment here that the concept of change involving time is a natural connection with physics, right? And I'd say yes, but I would say earth science and biology both have some natural connections there too, I would think.
Yeah, it's a natural for all disciplines. Engineering, life science, earth science, and physical science. That's probably why they call it a cross-cutting concept. And that's one of the strong pieces of this is what in the Next Generation Science Standards, the hope is that what's happening in the physics classroom leads to a deeper understanding in the biology classroom and in the chemistry classroom and in the engineering course. It's not that these concepts are learned one place and forgotten when they move to the other. A good example is energy and the way it's treated across disciplines. It's a cross-cutting concept, matter and energy, a cross-cutting concept, because it's important that students understand when we're talking about energy in physics, it's the same concept as when we're talking about energy in biology. So the cross-cutting concepts have great utility and power across all disciplines. And I have great hope that teachers across and faculties in schools will have conversations, that across grade levels will have conversations. And these are one of the pieces that fits across all grade levels are these cross-cutting concepts. They also turn out to be very valuable in terms of the literacy standards as well as the mathematics standards. The cross-cutting concepts conceptualize some of the ideas that students need to be powerful writers and to make sense of the mathematics they're expected to learn.
Okay, I'm jumping back to a question that I missed earlier. I don't know whether you feel qualified to comment on it. It says, will universities be using NGSS when working with pre-service teachers?
I know some of them will. I'm not qualified to answer that question. for all universities, but I know some that have already started on it. In fact, we have had a lot of conversation with pre-service providers, and they're very interested in the framework's vision and moving that forward because it has so much utility. The next generation science standards will be put in place in a number of states, and as soon as that happens, the university's teacher preparation programs are obliged to provide instruction that's consistent with the standards that are in place.
We're getting a lot of comments here about individual teachers here, excitement about the standards and how they're looking forward to them. The most recent one in Victoria coming in. I feel the NGSS will really spice up the way I teach, and I can think about that. It's actually reminding me of an analogy. I had been trying to work on something about the analogy between the different parts of the standards and relating it to some cooking, and someone said to me that the cross-cutting concepts, those are really the spices that you can mix and put together in a flavor. Different pieces here, so I'm reminded of that. I've seen that comment about spicing up the way you teach. Well,
I think it'll give this idea of the engaging students in performances are really going to add a lot to the instruction. But the cross-cutting concepts and practices are perhaps the outcome of the instruction. These concepts can be used with any core ideas. I mean, in any discipline. These are really the outcome of instruction. And students that don't go on in science, this becomes their utility. Students who have deep understanding of the cross-cutting concepts will have a greater understanding of what happens in their life related to science than knowing all the core ideas cold. It's really probably to most students the outcome of science instruction, understanding these cross-cutting concepts and the practices. But again, only if they're taken in the concept of all three dimensions working together.
You've mentioned some connections here about the relationship of science and NGSS to the Common Core State Standards a little bit. I'm wondering if with your experience as a state leader or district leader, if you have any suggestions for Pat's concern here about how do you get administrators to recognize that reading and math can be taught through science concepts?
I think many administrators recognize that already, but a great tool for convincing people of change is, in fact, doing it well. And not change that we've been talking about, the concept of reform or changing science or education. So having exemplary examples that can be done with students so that the children go home and tell their parents is one of the most powerful ways to change the vision for science education is through the students themselves having successful experiences. I know that one of the schools I work with is a STEM school, and they do a very nice job of making clear the connection between science and mathematics. Most of the mathematics are taught in this elementary school using science examples or data that the students have generated themselves. If you want to have a kid have deep understanding of data, of graphing, have them graph their own data, have them make sense of things using that graph through analyzing that data, and then construct an argument supported by the data that they generate.
David, a question here. Are there resources for us as educators to learn the big ideas, concepts and terms in stability and change? For example, I've seen static, dynamic, maybe stable versus unstable equilibrium, change and timescales, etc. I need to be educated myself. And so I don't know, would you have any recommendations of materials to read or pieces to look at that would discuss this more?
Yeah, I think that you could start with the cross-cutting concepts. Have a nice little appendix in the back of the Next Generation Science Standards. I really do think that the framework doesn't go deeply enough into the cross-cutting concepts to give the kind of examples that even we've talked about here today. And you're going to see more and more examples play out, grade level specific examples over time. I know that the professional development, I think we have a conference coming up in Arizona this fall and one someplace else where teachers have asked us to come in there with lots of examples. It's not enough to just simply talk in abstraction. They need specific examples and activities that can be used. George's work on lesson plans, the teachers are seeing a deeper vision of the standards through constructing instructional activities that engage all three dimensions. And then they begin to see a deeper understanding. So I think there's a number of ways that can occur.
Okay. Well, I think that's a good place for us to sort of conclude this evening on this. I want to thank Brett for what he's done here. I'm going to talk about a few resources NSCA has, and then we'll give you an opportunity to fill out your evaluation, and then Brett and I'll stick around for see if there's just a few last questions to work with here. But with that, let me just jump and point out that if you're looking and interested in the standards themselves, nextgenscience.org is the official standards page, and nst.org/NGSS is where you can find information about NSTA's resources around the standards and a lot of material there. I want to point out, we've mentioned a couple of times here, we have a member-only lister on NGSS and a discussion forum on NGSS in the Learning Center, and those are good places for us to be able to continue these discussions that we've been working with today. We're working our way through our series of web seminars. We've got 2 coming up. I want to point out that we've got one Thursday, June 6th, on structure and function. And it's going to be, we had to move that from earlier this year, or this month. So Thursday, June 6th. And then our final one on systems and system models will be Tuesday, June 11th, 6:30 to 8 p.m. Eastern. And if you're interested in learning more about any of the practices, any of these other cross-cutting concepts, we've got all these web seminars are archived, and you can go and listen to those, see the slides, take a look at the material that was there. We've been talking a lot about the framework that's in place here. You obviously can get a copy of that from the NSTA bookstore. The standards themselves, the National Academy Press will be publishing a print version of the standards that will be coming out this summer. You can pre-order that. And then you also have NSTA's Reader's Guide to the framework and Reader's Guide to the standards that there can be helpful to you in trying to understand these documents. Looking down the road here, we've got 3 area conferences: Portland, Oregon, Charlotte, North Carolina, and Denver, Colorado next fall. And we'll be in Boston in April 2014. And look forward to hope that some of you guys will make your plans to come there. There was a huge amount of information about the standards at our conference this last month in San Antonio. There'll probably be even more in Boston. A great chance to hone up on this. With that, I thank you all this evening for all your efforts, and a special thanks to Brett for coming in and doing this and helping us understand much more about cross-cutting concepts in general, in particular this one on stability and change. And with that, I will pass it off to Bryn.
Thank you so much, Ted, and I want to echo your comments and appreciation for Brett Moulding today. Fantastic presentation and lots of great discussion about this cross-cutting concept. Thank you as well to you, Ted, for facilitating our Q&A and discussion and for sharing information about NSTA resources on the NGSS. We would like to thank the sponsor of today's web seminar, the Carnegie Corporation of New York. And I wanted to thank the administration of NSTA for their support for web seminars. And before we wrap up, I wanted to point out our upcoming web seminar calendar. You can join us on June 4th for a program in our NASA Explorer School series, Center of Mass and Center of Pressure, Engineering a Stable Rocket. And then, as Ted said, come back with us on Thursday, June 6th for the next program in our Crosscutting Concept series on structure and function. And on June 10th, a special program about using the PD Plan and Portfolio tool in the Learning Center to document your professional learning. It is all available by going to learningcenter.nsca.org/webseminars. Thank you so much, everyone, for your participation today, and we look forward to seeing you again soon.